Given a potential energy diagram below for a harmonic oscillator, write an equation for the speed of the block in terms of the following variables. Well, the initial energy that's input into the system when the spring's initially stretched is constant and equal to the kinetic energy plus the potential energy. So E0 is always equal to 1/2 by kd squared, because that's the energy input into the system, and the kinetic energy at any point in time is 1/2 mv squared, plus the potential energy as a function of x as the block oscillates back and forth. So that will be the elastic potential energy stored in the spring. And then turning this equation around, for the speed of the block, we get v is equal to the square root of k on m by d squared minus x squared. So x must always be less than or equal to d, because you cannot have more energy in the system than what was input into it. So when the block oscillates back and forth, it can only go as far as minus d, so as to not exceed that initial energy. Given the potential energy diagram below for the harmonic oscillator, identify the equilibrium point and state whether it is stable or unstable. Well, recall that the force in the spring is equal to minus a change in potential energy. So when the slope of the tangent potential energy curve is 0, which is at this point, that's where the equilibrium point is. So recall that the potential energy stored in a spring is 1/2 kx squared, and therefore the force is equal to minus the derivative of this function with respect to x, so that will be minus kx. So when x is positive, the force is acting to the negative direction, and when x is negative, the force is acting towards the positive direction. So the force is always a restoring force that tries to restore that block back to the equilibrium position, and therefore this is a point of stable equilibrium. A 1 kilo rock is launched from a slingshot, and we're asked to derive an equation for the potential energy stored in a rubber as a function of x from the graph below. So recall that the force is equal to the negative of the change in potential energy with respect to x, so minus F is equal to plus du dx. And substituting for minus F, we get e to the lambda x minus 1 is equal to du dx, and then separating the variables, we get du is equal to e to the lambda x minus 1 dx. And then integrating both sides, and we integrate from 0 to x, so therefore the potential energy is equal to 1 on lambda e to the lambda x minus x, evaluated from 0 to x, and therefore u of x is equal to 1 on lambda e to the lambda x minus x minus 1 on lambda. A 1 kilo rock is launched from a slingshot from an initial position of 15 centimeters, and we're asked to find the speed of the rock when it reaches 10 centimeters, and we have the potential energy function. So the initial energy input into the system remains constant, so that's u at point 15, and that's equal to the kinetic energy of the rock, which is 1/2 by the mass by the speed squared, plus the potential energy of the rock when it reaches 10 centimeters. And therefore, if you evaluate u of 0.15 and subtract u of 0.1 from it, and flip this equation around, you're going to get the speed of the rock is 2.1 meters per second. The potential energy of a particle attached to a nonlinear spring is plotted below, and we're asked to calculate the equilibrium positions of the particle and state if they are stable. So we know that the force is minus the slope of the potential energy curve, which is equal to minus 1 plus 3 by x minus 2 squared. And if you set the force to 0, you're going to get two solutions to this equation. And that's going to give you the equilibrium points, which are at x is equal to 2 plus or minus 1 on root 3 meters. And now for this equilibrium point, we can see that the slope of the tangent to the curve is negative, So therefore, the force is positive. So it's going to point in a positive direction. And on this side, the slope of the tangent to the curve is positive, so the force is going to point to the negative direction. So therefore, the force is a restoring force, pulling that particle towards equilibrium. Now at this point, on the other hand, the slope of the tangent to the curve is positive here, so the force points in a negative direction. And over here, the slope of the tangent to the curve is negative, so the force points in the positive direction. So this here is an unstable point of equilibrium, because the force is pulling the particle away from the equilibrium point.